Morning Science 10. So today we're going to look at the law of conservation of mass. This is in your notes, but there's also a lab that we're going to do on the topic. As before, as always, you'll find the lab on Teams. You need to open it up. As I do the lab, I just need you to fill in the data. The notes for today's lesson are lesson 1.3. From your notes package on the topic of conservation of mass. So I'll just direct you to find that in your notes package. Maybe you want to pause the video now, and then we'll get going with writing down some key definitions and concepts. So the law of conservation of mass is a fundamental physical law that works in all chemical systems. It states that in any chemical change, the mass doesn't change. Now, when you have a chemical change, by definition, the chemicals are changing. You're starting with certain chemicals. There is a chemical change, and you end up with other chemicals. But in terms of mass, I think you can think of it this way. Imagine that all the atoms in the substances you start with are like a Lego car, something like that. Or maybe, let's say you have a Lego car and a Lego truck, and you want to make something new. You're bored with what you had. You take it all apart, and you put it together, and maybe you make two different vehicles. The point is, the number of bricks hasn't changed. All that's changed is the arrangement of those Lego bricks. In chemical change, it's the same way. The amount of matter measured as mass does not change. The arrangement of those atoms that make up the matter, that's what does change in a chemical change. Of course, this has not always been known to be a physical law. And like any physical law, it's open to testing. You can always say, I disagree. I'm going to conduct an experiment. Have a look for myself. That's what we're going to do today. We're going to do it on two different chemical reactions. I'm just going to focus on the notes here that I wrote up for you. You might want to add to what you already have. And then, of course, be having that Teams document open so you can work on this lab. So first of all, just scan the notes, and again, you can pause the video to write anything down that you find useful. Law of conservation of mass. Mass neither increases nor decreases in a chemical reaction in a closed system. And we'll get to that in a bit. Our goal, and you'll think about this in the lab, is to test the law of conservation of mass and examine how mass measurements are affected by having an open system. And we'll get to what that means in a sec. Here it is. Here's an example of a closed system. It's not the only possible closed system, but it's a simple example that we're going to examine today for the lab. The piece of glassware is called an Erlenmeyer flask. It's glass, kind of like a triangular cross-section. Notice that it has a rubber stopper. Energy can get in and out. The reaction system, what's happening inside there, can warm up or cool down. And you can feel that, or I don't know, as the temperature increases or decreases, you can feel that. But there's a rubber stopper at the top. Matter cannot go back and forth, only energy. This is a closed system. In this open system, I've taken that Erlenmeyer flask, which you're going to see an example of, and removed the stopper. Now, mass can go back and forth inside and outside of this reaction system through the top, obviously. In what form will it go? I mean, you could physically remove some, but there could be an involuntary aspect to that where there is a gas that passes back and forth. That would be the most common case where you could see the measurements of mass change. If the measurement of the mass changes from an open system, does this mean that the law of conservation of mass is wrong? No, it doesn't. All it means is that the matter left your system, or maybe someone dumped something in by mistake. Matter can go into the system as well. It goes both ways. So if your measurements of mass change for an open system, that's okay. It doesn't mean the law of conservation of mass is wrong, because when it's tested with a closed system where we know matter can't go back and forth, the finding is that the mass does not change. But again, we're going to examine that. We're going to examine this for two different chemical reactions. I used to do just the one involving acetic acid. Problem with that is you get high pressure inside the vessel and gas can get out anyways. Here, let me show you what I'm talking about. The first reaction that we're going to do in a closed system is this. It's described in your package. In black writing, iron 3 nitrate plus sodium hydroxide. Here, I'm going to focus on this. Iron 3 nitrate plus sodium hydroxide reacts to make iron 3 hydroxide plus sodium nitrate. That is the chemical reaction expressed as a word equation. In Science 9, you learned about how to make, how to draw chemical formulas. You may or may not remember that, but hopefully you're going to start to remember. Well, by now you'll at least have been reminded that chemical formula has chemical symbols that are organized in following certain rules and in a way that leaves no doubt from the reader about what chemical we're talking about. Two of them are used as reactants here. Reactants are what you start with. The iron 3 nitrate, the chemical formula for that is this. Every iron has a +3 charge here. Nitrates always have a -1 charge. You need one of the +3s to balance 3 of the -1s. Here is sodium hydroxide, NaOH. Sodium is Na, OH is hydroxide, OH minus specifically. They rearrange. We now have iron 3 hydroxide and sodium nitrate. I'd like you to notice the red numbers. What I've done there is something you haven't learned yet, and you're going to get into it later. I didn't want to write that down without doing it. What I did is I balanced the chemical equation. That's a very important exercise, and it's actually very relevant to the law of conservation of mass. Imagine this. What it's telling you is how much there is of each substance in the reaction. Think of this as 3 units of sodium hydroxide. Imagine the consequence for the law of conservation of mass if I had only 1 unit of sodium hydroxide. That would mean I had only 1 unit of hydroxide, and oh, look at this. I got 3 units of hydroxide on this side. That would violate the law of conservation of mass. Again, I don't expect you to understand that immediately because you haven't learned it yet. But I balanced the chemical equation specifically because that's what this lab is about. The second reaction is going to happen in an open system. I chose this one because it's a good illustration of the concept. This is a very familiar reaction to you. You've probably done it. Acetic acid plus baking soda reacts to make, see the arrow, sodium acetate and water and carbon dioxide. As formulas, acetic acid is this long thing right here, CH3COOH. Sodium hydroxide is also called sodium hydrogen carbonate. There's your makes thing here. That acetic part of the acetic acid is an ion. It's a negative ion. So this long thing right here is sodium acetate. H2O, of course, is water. And CO2, you'll know that. That's carbon dioxide. Notice that I didn't add any red numbers there because I don't have to. That's already a balanced chemical equation. That's the equation for the second reaction that you're going to see. That's the equation for what's happening in an open system. So all of that having been filled in, you might want to go back to that and pause it a bit, because what I've done there is I've answered the questions on the first page for you. You might want to fill that in. The other thing on the first page I'd like you to think about is, what is a reasonable hypothesis for this? If we assume that the law of conservation of mass is correct for our systems that we're working with, then you should be able to make a statement that makes a testable prediction. In other words, a hypothesis for what's going to happen when we examine mass in a closed system versus what's going to happen when we examine any changes of mass in an open system. Where might we see a change of mass? Where might we not? Now, of course, working in an open system, it doesn't necessarily mean that you will see a change in mass. It might not change there as well. The law of conservation of mass is fundamental in that way. But if the system is open, maybe it will. I'm going to show you the reaction. Hopefully this won't take too long. I've got everything in place and in order. I'll show you the equipment I'm using. When I do demo reactions, usually I've got some little changes that I end up making. Here's the equipment. These are Erlenmeyer flasks. These are 250 milliliter beakers. This is iron 3 nitrate. This is a 100 milliliter graduated cylinder with, well, sodium hydroxide in it. And this is a 50 milliliter graduated cylinder with iron 3 nitrate in it. Oh, and one more thing. These are my safety glasses. The first thing I'm going to measure will be the mass of the empty flask plus the stopper. I need this because later on I'm going to measure the mass of the flask plus the stopper with all the chemicals in it. So I need a baseline measure. You're going to see you're going to need to do a lot of calculation with this lab. So, here's my empty flask with the stopper. I turn on my centigram scale. And here is a value that you need to write down. Here it comes. 92.75 grams. That's the first row in your table right there. Now, we need to add to that 75 milliliters of the sodium hydroxide solution. So I'm going to press tare. I'm going to keep the stopper on there. Good. I think I'll get a funnel to make sure I don't pour any on my precious scale. Now, the mass of the sodium hydroxide solution as a reactant is 69.28 grams. You need to write that down. Now I'm going to set this aside. Oh, I made a mistake. I forgot about my funnel. My bad. The funnel, and you're going to need to subtract this because I'm not filming this video again. the funnel, which you will need to subtract from what I just told you, has a mass of 10.82 grams. From the 69 grams I just told you, you're going to need to subtract that value. Okay. Actually, here's what you could do instead. This makes a lot more sense. Cross out what you just wrote. You can if you want. Oh, no, don't do that. My bad. Forget what I just said. Do the subtraction. Subtract the mass of the funnel. Now we're going to work with our beaker. So we're going to put this beaker on here. This is the beaker that will have the iron 3 nitrate in it. I'm going to pour in my iron 3 nitrate, so I've pressed tare. I'm going to pour in my iron 3 nitrate. The mass of the iron 3 nitrate is 20.35 grams. Okay. Now, oh, that's bad. What should I do? I'm going to start that again. I should have done the mass with the beaker. I won't press tare. No big deal. All right. The mass of the beaker with the iron 3 nitrate is 85.98 grams. Let's work with that. Now we're going to pour the iron 3 nitrate from here into here, and then I'll give you the new mass of the beaker. This will go in the line that says mass of iron 3 nitrate after 25 milliliters poured from it. All right? What I'm about to tell you is going to go into that line. The value for that is 66.05. From that, you'll be able to calculate how much of the iron 3 nitrate I poured in. The 85.98 minus 66.05 will give you that. That will be in, that calculated value will be in bold. From the sodium hydroxide mass, which you will have been able to calculate, you'll be able to figure out the total mass of the reactants. The reactants are the things that are reacting. That is, you're going to get that by adding the mass of sodium hydroxide to the mass of the iron 3 nitrate. Next, I'm going to give you the mass of the products plus the flask and the stopper. First of all, let me draw your attention to the fact that clearly a reaction has happened. I started out with 2 clear liquids, and I ended up with a cloudy brown solution. There's a solid in the beaker. The total mass of the flask, products, and stopper is 171. Oh, let's make sure it's tared. Yes, it is. Is 171.08 grams. That's part 1 of the experiment finished. Now we're going to go to part 2. I'll try to avoid any little confusion. while we do part 2. So to fill in part 2, you need to go to the next page of the lab. You'll be filling in that table. You will be at the, while you are using the first table there on page 2 to fill in part 1, you will now be on this page right here, and you will be filling in the results here. All right. So first of all, I'm going to give you the mass of the empty flask. And that is 90.62 grams. The next thing I need to do is to press the tare or zero button and add about 75 milliliters of the acid solution and record the mass. Here it goes. I'm going to get a graduated cylinder. What you see in the bottle back here is 6% acetic acid. I mix it at that concentration specifically because that's the same concentration as you find in vinegar. Effectively, this is vinegar. Not bad. So next I'm going to give you the mass of the vinegar solution before the reaction. What I've done is I press the tare button here. I'm going to get that, I'm going to get a funnel again. I'm going to pour it all in. It'll be about 76 grams, maybe 78 or so. Let's have a look. My bad. Okay. The mass of the vinegar solution, and this is in, it's on the second line of the second table, is 86.91 grams. That is going to be in bold. My next direction is to add 50 milliliters of warm water to the beaker. I'll use this little beaker right here. All right, I'm going to press that. Now I'm going to get my warm water. Now I'm going to add about 5 grams of sodium bicarbonate. I'm going to tear this. Oh, that was dumb. Let's try that again. The mass of my sodium bicarbonate solution in the beaker is 59.58 grams. I'm stirring this up a little bit. Make sure that's dissolved. I'm then going to pour this into the flask with the vinegar in it. I'm going to pour this slowly. Because we know it's going to froth up. The amount of sodium bicarbonate I added was only about 5 grams. Again, I'm going to get the mass of this beaker after I've poured the solution from it. But first of all, let's make some observations of that reaction, just like you made observations of the first. Not surprisingly, and that's exactly what I didn't want to have happen. I am going to have to compensate for that because we've lost liquid. We need to figure out how much liquid we've lost, and we'll do that after. And you can add that liquid loss to the value. Because we're only interested in the gas. But I have a plan for measuring the amount of liquid that was lost. And you will need to add the value I give you to the mass of the beaker You know what, Science 10? This is not going well. I'm going to redo this whole thing. My apologies. You're all working on a computer. Some things don't go according to plan. I'm going to repeat this entire reaction. I'm going to do it in a bigger Erlenmeyer flask. All right. This is going to work. I got a mess to clean up afterwards, but you don't have to worry about it. That's my problem. We're going to take this whole scene and we're going to bring it to a different table. But I'm going to repeat the same kinds of observations. Let's go back here. Get things going. So whatever values I gave you before, you're going to need to delete those. But again, I'm thinking you're probably working in a computer file anyways, so it's not going to make any big difference to you. Here's my bigger flask. This is better work. I have a mass of this flask of 209.77 grams. Very thankful right now that I have such a good scale. Now, the next thing I'm going to do is press the tare button. And I'm going to add more acid. Going to use my funnel. And again, I'm going to pour in about 75 milliliters of acetic acid. This is one of the two reactants. I'm going to give you that mass. Not bad. Just under 75 milliliters. Good enough. I don't want to overshoot. I'm going to pour this into the flask. I get 74.99 grams. This really is row 2 of the second table, mass of vinegar solution before reaction. Now we're going to get a mass of sodium bicarbonate solution in the beaker. I don't need to tell you how much solid sodium bicarbonate I'm adding. I'm aiming for about 5 grams, but that is not a variable in your experiment. I'm now going to give you the mass of the sodium bicarbonate solution with the beaker that contains it. I will pour the sodium bicarbonate solution into here. Then I will measure the new mass of this beaker. I get 82.40 as my mass of this beaker plus the sodium bicarbonate that's in it. Now, you gotta wish me luck. I'm gonna pour my sodium bicarbonate solution into the acid. Hopefully it doesn't froth over this time. But you know what's gonna happen. Very nice. You can see the bubbles. If you were here, you'd be able to hear the popping sound of the bubbles as well. Now I will give you the mass of the beaker after the sodium bicarbonate was poured from it. That mass is 29.57 grams. Now let's get this funnel out of the way. Make this reaction finish up. Maybe you can even hear that reaction happening inside there. You will be able to calculate the mass of sodium bicarbonate that was added to the vinegar in the reaction by taking the value for row 3 and subtracting the value for row 4. You will also be able to calculate the total mass of the reactants by adding the mass of sodium bicarbonate to the mass of vinegar solution before the reactant. In other words, row 2 plus row 5 will give you the total mass of reactants, row 6. Next, I'm going to give you the total mass of the flask plus the products. That's the mass of this. And I get problem. So the scale has gone above its capacity. This is unfortunate, but I'm going to have to get around this. How should I do it? It's gone above its capacity. I might actually see if I can get this mass by some other method. This is not going well. Oh, I know what to do. This is 120 something grams. Okay, here's what I'm going to do. This flask weighs less. This small flask weighs less. This is what we'll have to use as a mass of the empty flask, the new mass of the empty flask. So you're going to have to go back and change your first row, but that's not a big deal. You can, or let's see, total mass of reactants, flask with products. Or in fact, you know what we can do? Hey, here's what we can do. We're going to go straight forward to the second to last row, calculated total mass of products. That will be this row right here, just above my thumb. This is called thinking on the fly, and hopefully it doesn't go too badly. So I'm getting the mass of this flask right here, but you don't need it. I'm going to pour these products into here. That will give us directly the total mass of the products. This isn't perfect. Realistically, yeah, a little bit of the products are going to get left behind in here. I can't really do anything about that because my scale went over its capacity. I'm going to let this drip a little bit. I get 124. Last little bit. The reaction's still continuing. $124.48 grams. Second to last row. Yeah, good enough. So from that, what you're going to need to do is you're going to need to take the mass of the vinegar before the reaction, the mass of sodium bicarbonate, add those two, that will give you the total mass of the reactants. The total mass of the products, I just gave it to you, 124.48 grams. you will take your result for row 6 and subtract the result for row 8, and that will give you the change in the mass during the reaction, if any. Now we are expecting some change in the mass during the reaction, but it wouldn't have been, now we can say it won't be from a bunch of froth spilling over the table. This is better. Those are all the results you need for the lab. The questions are, for each reaction, did you observe a chemical reaction or a physical change? What evidence do you have to support your thinking? Well, we saw a change in color, we saw a release of a gas. These are things we expect from chemical reactions. Why would there have been a physical change? We didn't add any heat, we weren't boiling it or anything like that. And the change in the texture definitely is evidence for a chemical change. You will then be looking at how the final mass of the products in your first system compared with the starting mass, and then doing a comparison of how the final mass and the starting mass compared for part 2. Question 3, list each reactant and indicate its state of matter. The reactants are what I showed you before. They are on the left-hand side of the reaction equation. So, for example, for the second reaction, the one we just did, the reactants were acetic acid and sodium bicarbonate. How do they support the law of conservation of mass? Really here you want to focus on what happened with the closed system and assess how that applies to the law of conservation of mass. What substance is responsible for the change in mass in part 2? Well, we're looking for something that is a gas. Was there a gas that left the flask? That's probably going to be your answer. And if there's a small difference, does this mean the law of conservation of mass is wrong? I think we can agree that despite the best of my efforts, it wasn't perfect, the reaction that we just did, and so we can't rule out the possibility that there might have been some slight differences that you might observe. But you should see a pretty big difference in the mass loss comparing the part 2 versus the part 1. That is all you'll need for completing the lab conservation of mass. Thank you.